Okay, let's get to this next example. F of x equals x squared over x squared plus 1. So we're looking for vertical asymptotes and wholes. For wholes, what we would want to do is start by factoring the numerator and denominator and then see if anything would cancel. So this x squared plus 1 actually doesn't factor over the real numbers. It looks like it would be difference of squares, but it's not. It's sum of squares. So it's not going to factor. And since it won't factor, nothing's going to cancel. So there will be no wholes. So wholes, none. Let's look at vertical asymptotes. So vertical asymptotes. We would set the denominator equal to 0. And then if we move that 1 over, x squared equals negative 1. Take the square root of both sides. And we have x equals plus or minus. The square root of negative 1 is I, right? Which is a non-real number. And since we graph over the real number line, the real numbers in our coordinate plane, there's going to be no vertical asymptote on our graph. So there is no vertical asymptote as well. So that can happen. Let's look at our third one. Y equals x squared minus 9 over x squared plus 4x minus 21. So I apologize for all the noise going on in my house. There's 2 teenagers and 3 dogs out there. Okay, we will start by factoring. So we get y equals, this is difference of squares again, so x plus 3 times x minus 3. And then the denominator will factor to be x plus 7, x minus 3. Okay. So now that we have that factored, we see that we have a common factor that we can cancel. So I think of it like I'm making a whole by taking this out of the function. So this is going to be a whole at the x value that we get, x minus 3 equals 0. So x equals 3. So 3 comma some other y value. Then we have a new function. After we simplify, the new function is going to be y equals x plus 3 over x plus 7. So what this function is going to be is the same as the original function, except for we took out the whole. So we should be able to graph this entire function, but when we put it on our graph paper, we're going to put a whole at an ordered pair here. So the ordered pair that we're going to put this at is going to be y equals, we're going to replace 3 in for our x's. So 3 plus 3 over 3 plus 7. So that is what, 6/10 or 3/5. So the whole is going to be at 3 comma 3/5. Then to get the vertical asymptote, we are going to set the denominator equal to 0. And the one that we want to set equal to 0 is the new denominator. So I'll go ahead and add in there, set the new denominator equal to 0. So x plus 7 equals 0 gives us x equals negative 7. So we've got a whole at 3/5 and a vertical asymptote at x equals negative 7. So let's go ahead and see what our behavior is like, what our function is doing on both sides of x equals negative 7 by doing those limits, right? So here we've got our coordinate plane, and we're going to go over to x equals negative 7. Here's going to be my vertical asymptote, x equals negative 7. And I want to look at the left-hand side and the right-hand side of x equals negative 7. So on the left, we'll be looking at the limit as x approaches negative 7 from the left of our function, which is x plus 3 over x plus 7. And then on the right side, we want to look at the limit as x approaches negative 7 from the right of x plus 3 over x plus 7. So remember that when we do that, we're going to pick a number that's a little bit on the left-hand side of negative 7. So like negative 7.01. And that's what we're going to plug in for the x value. We don't really care what the total value is going to be. We're just looking at what is the sign. So if I take negative 7.01 plus 3, that's going to give me a negative number. If I take negative 7.01 plus 7, that is also a negative number. So that is going to end up being positive. So this limit is going to go towards positive infinity. So on the left-hand side of this vertical asymptote, the function is headed up towards infinity. Let's look on the right-hand side. On the right-hand side of negative 7, like maybe negative 6.99, so not quite at negative 7, then we're going to plug that in. Again, we don't care about the number, we just care about the sign. So negative 6.99 plus 3, that is going to be negative. Negative 6.99 plus 7, that is positive. And negative divided by a positive is a negative. So that will be negative infinity. So on the right-hand side of negative 7, the function is headed down towards negative infinity. These arrows and stuff that we're drawing are going to make more sense when we start putting them all together to actually draw a rational function. But for now, we're just doing the bits and pieces. So the next little piece we're going to talk about is horizontal and oblique asymptotes. Now, these are going to help with end behavior. Remember that in our rational functions are a polynomial function over another polynomial function. And what we're going to be using for all of these problems here, all of these decisions about these horizontal and oblique asymptotes, is the degree of the numerator, and that they call n, and the degree of the denominator, which they call m. So what we're going to be doing is comparing the degree of the numerator with the degree of the denominator. So there's only going to be a few possible options that we'll look at. So the different possibilities are for the degree of the numerator to be smaller than the degree of the denominator. The degree of the numerator and denominator are equal. The degree of the numerator is 1 more than the denominator, or the degree of the numerator is 2 or more higher than the denominator. So we'll look at each one of these separately. Our first one, the degree of the numerator is less than the degree of the denominator. In this case, we are going to have a horizontal asymptote at y equals 0. So what's going to end up happening is that the left end and the right end level out at 0. So these functions do some crazy stuff in the middle, but at the ends, they are going to kind of level out. Like, if you look at them from a far enough distance away, they'll look like the line y equals 0. And so the way that we describe that end behavior is to say that the left end, so for the left end, remember we had done this before, the limit as x approaches negative infinity of our function is going to equal 0 because it's leveling out to be y equals 0. And then the right end, remember we had said that limit as x approaches infinity of the function is equal to 0. We'll see examples of these as we get into section 5.3, where we get to actually put all of this together and make graphs. Then we have a horizontal asymptote if the degrees are equal to each other. So in that instance, what we're going to do is we're going to use the leading coefficient of the numerator and the leading coefficient of the denominator to find the equation for that asymptote. So if the degrees are equal, we're going to have a horizontal asymptote. Wow. It's going to be y equals, we divide the two leading coefficients. So the leading coefficient of the numerator over the leading coefficient of the denominator. And then we simplify that fraction, so it ends up giving us y equals some number. So then the end behavior, when you have a horizontal asymptote like that, is going to be that the left end, so the limit as x approaches negative infinity of our function, is going to equal that number that we got, and the limit as x approaches infinity of that function also equals that same number. So instead of leveling out at y equals 0 on the ends, these ones level out at y equals whatever that number is. So it's kind of like a vine, like it does some whatever stuff in the middle, but at its ends, it's going to kind of follow along the horizontal line, y equals 0 in this case, and y equals that number, that ratio in this case here. Then we have when the degree is 1 higher than. So like if the numerator is squared, then the denominator would be to the first power. If the denominator is to the fifth, the numerator would be 1 higher than that to the sixth. So that's probably worth writing down. So the numerator is 1 degree higher than the denominator. And this kind is not going to give us a horizontal asymptote. It's going to give us an oblique or slant asymptote. So instead of being the equation of a horizontal line, this is going to be the equation of a line that has a slope and a y-intercept. So y equals mx plus b. And the way that we find this is by long division. So we're going to have to do some long division in these problems. And then the last type that we're going to talk about is when the degree of the numerator is 2 or more higher than the degree of the denominator. And in this case, for what we're doing in this course, we're just pretty much going to say that there is no oblique asymptote and no horizontal asymptote. So we'll say there is no oblique asymptote and no horizontal asymptote. But if you need to, you can approximate the end behavior by using a power function. And the way that we find the power function is by taking the ratio of the leading terms. Oh, it says that right here. So never mind, you didn't have to write that. Hopefully you noticed it before I noticed it. One thing I definitely want to point out, and that is that functions are allowed to cross horizontal and oblique asymptotes. They are not allowed to cross or touch vertical asymptotes, but it's possible for them to either cross through or touch a horizontal asymptote. I will be showing you how to find that information out in section 3. All right. I believe this is the last page of 5.2, and we are going to be figuring out what kind of asymptote we have and then getting the degree of that asymptote. So each time when we do this, we want to identify the value of n and the value of m. So in this case, the value of n is the degree of the numerator, which is 3. The value for m is the degree of the denominator, which is 5. So for this problem, n, which is 3, is lower than m. So here I have n equals 3, m equals 5. Since 3 is less than 5, that tells me that n is less than m. So then I look at my rules over here. Conveniently, when n is less than m, that gives me a horizontal asymptote at y equals 0. So this function would have a horizontal asymptote at y equals 0. That's all we're doing for this section. What's our next one? The degree of the numerator is 2. The degree of the denominator is 2 as well. So here I have n equals 2. Here I have m equals 2. Since 2 equals 2, that's the one where n equals m. So when n equals m, we're going to have a horizontal asymptote at y equals the leading coefficient of the numerator divided by the leading coefficient of the denominator. So this guy has a horizontal asymptote at y equals 8 from the numerator over 4 from the denominator. So that gives me y equals 2 for my horizontal asymptote. Next up, we've got the degree of the numerator is 4, the degree of the denominator is 3. So that's telling me the degree of the numerator is 1 higher than the degree of the denominator. So here, that's n, m is 3. So I've got 4 equals 3 plus 1. So that's where we get this, which is going to be that oblique or slant asymptote. And that means we have to do long division. So here we go. In polynomial long division, we want to start with the numerator inside the division symbol. So 3x to the 4th minus x squared on the inside, and then x cubed minus x squared plus 1 on the outside. Okay. Then when I do polynomial long division, I will talk you through it. I am going to start by looking at the first term on the inside, so the dividend, and the first term on the outside, so the divisor. And I want to basically, I'm going to figure out what I would need to multiply my x cubed by so that I get 3x to the fourth. So I know this pen's not going to work very well, but it's what we got. So what I do is I take my 3x to the fourth and I put it over x cubed. So I'm going to go off to the side, 3x to the fourth over x cubed, which is going to give me 3x. So I'm just working with these first terms. Then I'm going to multiply 3x times my entire divisor. So I'm going to multiply that by x cubed minus x squared plus 1. And that's going to go on this row right here. So that will be 3x to the fourth minus 3x cubed plus 3x. Okay. Next thing I'm going to do is change all of the signs in this bottom row. So I'm doing that instead of subtracting because I always mess it up if I subtract. Whoops, that was already positive, so I already messed it up. So change that to negative, change that to positive, change that to negative. That allows me to add instead of subtracting, and I'm better at adding than subtracting myself. So then I'm going to do 3x to the fourth minus 3x to the fourth. Those drop off. They cancel to 0, which is what I was after. There's no like term to add the 3x squared to, so it just is by itself, 3x squared. And then negative x squared, there's nothing. Oh, haha, that was 3x cubed. Maybe. There's nothing to add the negative x squared to, so it just drops down. And then the negative 3x also comes down. Then I'm just going to repeat that process again. So I'm going to take this first term here divided by that first term again in the divisor. So I do 3x cubed over x cubed, which is going to give me 3. I multiply that by the divisor, x cubed minus x squared plus 1, and that's going to go on this line. So I'll have 3x cubed minus 3x squared plus 3. And then again, I'm going to change all the signs. So this now becomes negative, this becomes positive, this becomes negative. And I'm going to add straight down. Three x cubed and negative 3x cubed, those cancel. 3x squared minus x squared is 2x squared. And then nothing for negative 3x to combine with, and negative 3 there. Now, I already have my oblique asymptote. You just don't see it yet. Because as I'm going, the oblique asymptote is collecting by what I got here. So up at the top, I would put this 3x up here. So 3x, this is part of my oblique asymptote. And then this is also part of my oblique asymptote. So 3x plus 3, and that's it right there, guys. It's y equals 3x plus 3. You might need some more practice with polynomial long division, because I know it's been a hot minute since you've done it. So let me know if we need more practice with that. Okay, our last example here, we have f of x equals 2x to the fifth minus x cubed plus 2, and then that's over x cubed minus 1. So let's compare the degrees. The degree of the numerator is 5. degree of the denominator is 3. So that means that the degree of the numerator is 2 or more higher than the degree of the denominator. So here I've got n equals 5, m equals 3. So remember this one, that if n is greater than or equal to m plus 2, so 5 is greater than or equal to 3 plus 2, which gives me 5 is greater than or equal to 5, then that means there is no horizontal asymptote, no oblique asymptote. But remember that we can tell how the ends behave. The ends are going to behave like the power function if I put the leading term over the leading term. So if I put y equals, the leading term in the numerator is 2x to the 5th. I'll scoot that over in a second. Over the leading term of the denominator, which is x cubed. So y equals 2x to the 5th over x cubed, or the ends behave like y equals, that simplifies to 2x squared. So the ends of this rational function will both be going up, just like the polynomial function y equals x squared.